Hello and welcome to the Ways of Math. I'm your host Dan the Math Man. Today we're going to continue our series on the Introduction to Sets. This is part 7 of a multi-part series, and this one is on Venn diagrams with 3 sets. Okay, so in this video we're going to describe the regions of the 3-set Venn diagram, as well as an approach to constructing such a Venn diagram, and then we'll use an example of how to construct a 3-set Venn diagram. So today we continue our discussion on how to use Venn diagrams to describe and solve set problems. This time we'll be using 3 sets. And while Venn diagrams can be used to solve set problems that have more than 3 subsets, it becomes increasingly difficult to interpret the individual regions. As we'll see in the next slide, the number of regions grows exponentially for the number of sets that we have. We will also begin to discuss a basic approach to setting up all Venn diagram problems. So this even applies to the 2-set Venn diagrams. But even if we did have 3 like we're going to do in this video, or if we had 4 or 5, we could still use this basic approach that we're going to talk about. Okay, so this is what a 3-set Venn diagram looks like. We have our sets A, B, and C here. Okay, and so we notice this time there's 8 regions, right? So there's 1, 2, 3, 4, 5, 6, 7, and 8, right? With the 2-set Venn diagrams that we did in a previous video, right? We had 4, right? In this one we have 8. So as it turns out, for n number of sets, right? So if we have 2 sets or 3 sets or 4 sets, etc., we're going to end up with 2 to the n number of regions, okay? Which is why if I had a 4-set Venn diagram, I would then have 16 regions, and a 5-set Venn diagram would have 32 regions. So you have to get a little bit more creative in how you construct the diagrams to make sure that you can read all of the regions, and you can also make sure that you actually get all the regions, right? Because after you start getting to 4 and 5, you can no longer use like ellipses or circles. You have to start getting a little bit more creative with how you set it. I mean, you could use ellipses, but they will end up not being all centered like this. But that's for another time. Okay. So first, let's discuss the regions. Okay, so region 1 represents elements in A that are not in B and C. Very similar to how the region 1 was for the 2-set Venn diagram, right? So we see here it's contained in the set A, but it's outside of B and C. Formally, we can write this as A intersect the complement of B intersect the complement of C, right? Because it's in A, and it's not in B, and it's not in C. Region 2, notice this is inside the overlap of B and A, but notice it's outside of C. So this is what's shared by A and B, but is outside of the set C. And we write that as A intersect B intersect the complement of C, or we can read it as A and elements in A and B and not in C. Region 3 represents elements in B that are not in A and not in C, right? So very similar to region 1. This is what's in B but is not in any of the other sets. And again, we can write that as A complement intersect B intersect C complement, right? Because this is elements that are not in A, and they're in B, and they're not in C. Region 4 represents elements in A and C that are not in B, right? So it's very similar to region 2 here. It overlaps 2 sets, but doesn't overlap in the 3rd set. And that can be written as A intersect B complement intersect C, right? Again, we can read this as A and not in B and C, so elements in there. Okay, region 5, this is the intersection of all 3 of the sets. So this is where all 3 sets overlap. So these are elements that are in A, B, and C, or formally we can write it as A intersect B intersect C. And we can read this again as A and B and C, so elements in A and B and C. Region 6, similar to 2 and 4, are elements that are in both B and C, but they're outside of A. And we can formally write that as A complement intersect B intersect C, right? So again, elements not in A and in B and in C. And the last 2, so region 7, similar to 1 and 3, are the elements that are in C but not in the other sets. which again we can write in a similar fashion as A complement intersect B complement intersect C. And again, read it as elements not in A, and not in B, and in C. And then lastly, region 8. This is our region that's outside of all the sets, all these subsets of U. So these are elements that are in the universal set that are not contained in any one of these subsets. So formally we can think of they're not elements in either A, B, or C. And formally we can write this as the complement of elements in A or B or C. So the complement of A union B union C. Okay. Now let's take a look at an approach of how to construct this, right? Because as we get to these bigger sets, there's a little bit more work that goes into the construction of these sets. Okay. So the first thing to do is to determine the elements to be placed in region 5, right? Kind of similar to how we set up the two-set Venn diagram. We started with the intersected region, so the innermost intersected region, right? And then we kind of worked our way out, and that's the same principle behind this. So we start with elements that are common to all three sets, A intersect B intersect C, as we see here. And then we kind of proceed by spiraling out, right? So we kind of start working our way outward. So this is the intersection of all three sets, and we work out to the intersection of exactly two sets, which is the region 2, 4, and 6. So elements in A and B, right? So elements in A and B are these two regions. So the way we would find this was we want to know what's in A and B, and then subtract the elements from from 5, I'm sorry, and then we get the elements in 2. Similarly, in 4, right, these are the elements in A and C, but then we subtract off the elements that are already in region 5, and that's what's left over goes in region 4. And then similarly for region 6. These are the elements that are in B and C if we take out the elements that are already in region 5, which is shared by all the sets. And then we continue to spiral outward again. So now that we have these innermost sets, all these overlapping sets, we can now determine what's in regions 1, 3, and 7 here. Again, if we know the cardinality, or if we know the elements that are in A, right, then we can remove the elements we've already placed because they're already in here, and then whatever's left over from set A goes into this region 1. Similarly, for region 3, we've already placed elements in here, so all the elements from B have already been placed in here, except for whatever's left over in the set B. Those remaining elements go in here. And then, of course, in like manner for region 7 here. Now, lastly, all the remaining elements from the universal set that have not already been placed in any of these subset regions, all those go into region 8. And then we'll have our completed Venn diagram after that step. So let's take a look at an example. So suppose our universal set is all the elements, all the positive integers from 1 to 18. And suppose A is the set 1, 7, 8, 9, 11, 12, 13, 14, 18. Set B is 2, 3, 5, 6, 7, 8, 13, 14, 18. And set C is 1, 3, 5, 8, 10, 12, and 13. Okay, so let's begin. So as we described in our approach, we want to determine what elements are in the region 5. So what's in all three of these. Right, so we notice that if we go through these sets, we see that 8 is in common to all three sets, as well as the element 13 is in common to all three of those sets. So we're going to put 8 in here and 13 in here. Now, since 8 and 13 were already placed in region 5, kind of a good note to keep as you construct these Venn diagrams is to kind of X them out as you go, right? So notice I've X'd out element 8 and elements 13 in all A, B, and C, but I've also done that in the universal set. So that way, whatever is left in the universal set, I know that I still have work to do because I haven't placed all the elements in the universal set somewhere in one of these regions. So as per the instructions, we kind of do our spiral out, right? So we already have the center, so we move out to region 2 here, which are the elements that are shared in A and B that I haven't already placed in region 5. So I look at just the remaining elements of the ones that are not scratched out, and what's left over in A and B that are in common. And we see here element 7, 14, and 18 are in both A and B. And so we place those then in region 2. And then in like manner, we X those out from both A and B, as well as the universal set. Right? So we're slowly making progress through this universal set. So again, we look at now region 6, right, as per our instructions. And we look at now the elements that are in A and C that have not already been marked off. So we see that the elements 1 and 12 are shared in common with both A and C. So those go into region 4. Now we mark those off of our set, so they're out of our universal set, they're out of set A, set B, and set C. And we move on to region 6 here. So what's left over that's in common to B and C that we have not already been placed, right? And while notice these sets are dwindling. This is why marking them off as you go makes it much easier to read these sets, especially if they're bigger sets. So we see now that 3 and 5 are shared by both B and C. So they're in common, so they're in the intersection there. So we place those in region 6 here. Continuing on with that, we've got all these kind of inner sets, or these inner regions out of the way. Now we're looking at whatever's left over in sets A, B, and C. So we start with region 1 here. So what's left over in set A that I haven't already placed in any one of these regions? Those are the elements 9 and 11. So I place those in region 1. And notice again, I X'd out all the ones I used in the previous step. Now we move on to region 3. So this is whatever's left over in B that I haven't already placed. And again, since everything's X'd out, this makes this very easy to read. Elements 2 and 6 are the only thing left over. So those go into our region 3 there. Next, in region 7, this is all the elements left over in set C that have not already been placed. And again, thanks to all of our strikeouts, it's easy to read what's left over in C, namely the elements 10 and 16. Now, since we were keeping track, and we X'd out everything as we went along, both in those sets, the subsets A, B, and C themselves, but also in the universal set, we see that now the only thing that's left over in the universal set that haven't already been placed in A, B, and C are the elements 4, 15, and 17. And lastly, those go into region 8. So here's our final answer. Okay, there's our universal set. There's our subset A, B, and C. And we see that all the elements are placed in here. Now just one final check to make sure we haven't duplicated anything. We can count through the universal set if that's possible, which in this case it's fairly easy to do. All the elements 1 through 18 should be placed somewhere and only placed once. So we see element 1 is right here, followed by 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, 12, 13, 14, 15, 16, 17, and finally 18. We've counted through all the elements in the universal set. They all have a place in one of these regions, and none of them were double counted. Now, this can also be done. Remember when we talked about Venn diagrams the first time, sometimes we don't put necessarily the explicit elements, but we put the cardinalities of the elements, or the cardinalities of each of these regions in the appropriate set. So if we had done that, then we would have put 2 in here, we would have put 3 in here, 2 in here, 2 in here, and etc. So we could have done that. And if we had done that, then we would have noticed that if I added up the cardinalities of each of these regions, 2 plus 3 plus 2 plus 2 plus 2 plus 2 plus 2, and finally plus 3, the cardinalities would, or the sum would result in 18, which is the cardinality of the universal set. So we could have done that as well if we didn't, if our particular application didn't require the explicit elements in the Venn diagram, but just the cardinalities of each of the regions in the Venn diagram. Alrighty, thanks for watching. Please be sure to subscribe, and please leave any comments or suggestions in the comment box below. I hope you enjoyed it. Thank you, and have a wonderful math-filled day.